Okay, this next section is about vector spaces and subspaces. Um, and before we start talking about vector spaces, well, let's read this first sentence here. It says a vector space is a non-empty set V of objects called vectors, on which we define two operations called addition and scalar multiplication of real numbers, subject to the 10 axioms listed below. And so let's stop right there. A couple things. First thing is, we're talking about vectors here, but we don't necessarily mean vectors in Rn. So vectors right now just mean elements of a vector space. So for example, in 2 pages, we'll look at vectors that are polynomials. And those elements will be members of a vector space, but they're not necessarily vectors in Rn. The second thing I just want to point out is when it says we have 2 operations called addition and multiplication by scalars, those 2 operations can be defined differently than we're used to. So we're used to certain rules of addition, like when you would add real numbers, you add the values together, or when you add vectors, you add the individual entries together. But there can be other rules for addition and multiplication, and all this is saying is that this space has some rule for addition and multiplication. Now the ones we'll see are going to usually be the standard one, but I just want to be clear that you can redefine addition and or multiplication in different ways. And this is just saying that this space has some definition for these addition and multiplication. I'm just going to play around with the light real quick just to see if I can improve what's going on here. Is that too bright? Let's see what happens. Is that too bright when I look at things? Let's see if I try this. Maybe I'm going to stick with that. Okay, and so once we have a vector space, or we have a bunch of vectors in a space, and we have addition and multiplication satisfied, the idea is if these 10 properties are satisfied, then this space is called a vector space. And I'm going to go through these all one at a time and just sort of mention what they're saying, but just note that within these definitions, U, V, and W are vectors, and we know they're vectors because they're bolded. And then within the definitions, C and D are going to be scalars, and so we know they're scalars because they're not bolded. And so the first property says when we have 2 entries and we add them together, so U and V are in the space, when we add them together, it's still in the space. And so this is closed under addition is what we would say there. The second element says we can change the order in which addition takes place. So U plus V equals V plus U. Number 3 tells us we can change the order in which things are, the way things are grouped when we add them together. So this is associativity property. Number 4 tells us that there has to be some version of 0 in this space such that when we add that number using our definition of addition to any vector, it stays the same. And that's important because we need a 0, and then that appears in number 5. So number 5 tells us there has to be, for every vector in the space, there's some negative version of that vector, such that when you add U and the negative version together, you get the 0 vector. And when I say the 0 vector, I mean the 0 vector that was just described in 4. So 4 sort of tells us, okay, there is a 0 vector, and then 5 tells us this is called the additive inverse. You can get back to the 0 vector with some other element in the space via addition. So in other words, number 5, the way you might see that described some places is called the additive inverse. It has to exist. Number 6 tells us that scalar multiples stay in the space. So if U is in the space and we multiply it by some random scalar C, then CU is still in the space. 7 and 8 are like distributive properties, right? So these 2 things are distributive properties. And 7 tells us we can distribute a scalar through the sum of vectors. And number 8 tells us we can distribute a vector through the sum of scalars. Number 9, again, is we can rearrange the order in which scalars are multiplied by vectors. And number 10 is a multiplicative identity property. It tells us that there's some vector 1 in the space that we multiply it by U, any vector in the space, it stays the same. I'm sorry, u is a scalar, and 1 is a scalar in this. So this is called the multiplicative identity. And so the idea behind this is if you want to show something is a vector space, then it's a little bit tough, not tough, but it's a little bit arduous, I might say, because you have to go through all these different properties and show that they all hold, right? So to prove something is a vector space, you have to show all the 10 axioms are true. But if you want to show something's not a vector space, you just need to show that one of these things fails. And so it's sometimes easier to show something fails because you only have to go through one of them. And so we're going to do some examples of this. I'm going to show that go through Rn and show that Rn is a vector space for a specific n, and we'll show an example of one that's not a vector space on the next page, and then, as I mentioned, we will look at an abstract vector space, this set of polynomials, on the third page here. Okay, so the first thing you should know is that all spaces Rn are vector spaces, right? So Rn, you pick a specific n, and it tells you how many dimensions that we're in. So, for example, R2 is the normal x1, x2 space that we're used to with the Cartesian plane there. If we wanted to think about R3, it would have 3 axes, right? x3, x2, x1, right? You could have all different kinds of these things. R4 we can't visualize, but it would have 4 entries, right? x1, x2, x3, x4, etc. And so all of these spaces, Rn for any n, is a vector space is what this is showing, what this is telling us. And so let's go ahead and pick a specific R, just an easy one. Let's do R2, for example, and we'll show that R2 specifically is a vector space. And so we'll start that at the bottom of this page, and then we're going to show all 10 of these properties, and so it's going to carry on to the next page. Just be aware of that. So let's go ahead and show that R2 is a vector space. And so looking at the definition above, the V in the definition above is R2. And so we're going to go through, right, so V in this case that I'm saying right here is R2. Let's pick a U, a W, and a V and in the space, and then we'll go through each one of these properties and show that they all hold. And so let's pick a U. So let's U be AB. We could let V be some other two-dimensional element. How about DE? And let's let W be FG. Each of these things is in R2 because they have 2 elements in their vectors, right? And so again, what we're going to do is we're going to go through each one of those properties and see that they hold. I'm just seeing there's some shadows here. Would that be helpful if I turn the lamp back on? Maybe that is better. Okay, so I'm going to do that. So number 1 tells us we should be able to add 2 vectors together and it should still be in R2. And so let's add U and V together and see that it stays a two-dimensional object. So U plus V would be AB plus DE, right? We're adding the 2 vectors. And when we add the 2 vectors together, we just add their elements. And so we get A plus D, B plus E. And this is still a two-dimensional object, right? A plus D would be some new entry in the first entry, and B plus E would be some new second entry. And so this is still a 2 by 1 vector. Thus, it's still in R2. And so, check. We showed that property holds. We took 2 arbitrary vectors in the space, we added them together, and we got another arbitrary vector in the space, and so that is still in the space. Okay. Just trying to play with the light here a little bit. Let's show the second property. The second property says we should be able to change the order of addition on vectors. And so let's add 2 vectors together again, U plus V. And let's show that you can change the order. So we already know when we add them together, we get this. And once we have this is just real numbers being added inside of a vector. And so we know that we can change the order of real numbers being added, right? So we can do this, in other words, d plus a, e plus b. And since we just changed the order, we can break it apart into two separate vectors, de plus ab, and now this is v plus u. Check. Right, so we write down, specifically the elements that, the element-wise representation of u plus v, and then we just change the order of those real numbers once we have that representation and split it up so that we started with u plus v, but we ended with v plus u, and so we showed the second property holds. The third property is very similar. We're going to change the order in which things are grouped. And so we're going to start with the left-hand side, but then we're going to regroup things, and then it'll end up looking like the right-hand side. And so for this one, we need u, v, and w. So let me do u plus v grouped first, plus w. So if we did this first, we would add u plus v first, and so we would still have the a plus d, b plus e, right? That's our first, that's our u plus v value. And then w is going to be fg. And so then when we add all of them together, they're just real numbers, three real numbers in each entry being added. And real numbers being added together, we know we can group them any way we want. And so in other words, I could group d plus f and e plus g together, and then break this vector up so that v and w then get grouped together when they're added. Right, so let's break this up like this. And now this looks like u plus v plus w being grouped. And so we regroup things element-wise by breaking it down like that. And so we've shown the first three properties here. I'm going to flip the page and show 4 through 10. I'm trying to be careful about this, go through the details here, and you can see that these things can be a little bit tedious sometimes if you want to show all 10 properties. The nice thing is, once we get to, we're talking about vector spaces right now, once we get to subspaces, it's a little bit easier to show those. A little bit quicker, I should say. Okay, so before I flip the page, the next thing we're going to show is the zero vector. We're going to figure out what the zero vector is in the space. It's some vector such that it doesn't change a vector when we add it to an arbitrary vector. And so let's pull out the second page and look at that. So number 4. Now in R2 and in Rn in general, the zero vector is what we think it is. It's 0, 0, right? So the zero vector in R2 would be 0, 0. And we know it's 0, 0 because when we add it to some arbitrary vector, like u, for example, we just end up adding 0 to both the elements, which keeps it the same. And so in Rn, 0 is just the zero vector, but in other spaces it might be a little bit different. And so there just needs to exist some zero vector. Number 5 tells us we need to have an additive inverse that gets us back to that zero vector when we add it to an arbitrary element. And so if we're thinking about 5, if u equals ab, which we know because we've been dealing with u quite a bit, then minus u, the thing we would need to add to that to get to this zero vector right here, would be minus a minus b, right? Because when we do u plus minus u, that should be a minus u. Let me make that a little more legible here. We end up doing a minus a, b minus b, of course, and so we get to the zero vector when we do that. And so that's doing a minus u, just putting a negative sign in front of your entries is the negative vector in this space, is the additive inverse. Number 6 tells us we should be able to multiply by a scalar and stay in the space. So you might want to look at number 6 and see what that looks like. We want to multiply c times u, where c is an arbitrary scalar, And that would look like this. And this is still a 2x1 entry, right? So still a 2x1. Thus, it's still in R2, which is our space B. Okay, we're more than halfway there. Now we want to do some distributing. 7 and 8 take a little bit longer to write out because we have to write out some distributed properties. Let's look at 7 and 8. Let me just remind you what those two things are. We're going to distribute a scalar through the sum of vectors and then a vector through the sum of scalars and see that you can do that distribution. But we're going to write out the entries carefully so we can show that, so we can be confident about it basically. So in other words, when we do C times U plus V, we know that that's going to end up being C times A plus D, B plus E, excuse me. And then we know that we can distribute a scalar into a vector. And so this ends up being AC plus DC, BC plus EC. And then we can split this thing up now and show that it actually distributed, right? So we can split this up into AC BC plus DC EC. And then we can factor out a C from both of them. And then we're just about there. Because once we have it looking like this, this is C times a vector U, C times a vector V, and that's exactly what we were trying to show. But we take it element-wise, right? So we're not really sure we can, the idea is like we're not sure we can do it with this vector representation, and so we break it down into the individual components, which are just real numbers, right? Everything in this, every individual thing that I'm circling right now is just a real number, and we know we can do things like distribute and change order with real numbers, and so then we mess around with the real numbers, factor things out, and then rewrite it the way we were hoping to show. And number 8 is very similar the way that works. You're just starting with two scalars being added instead. And so this is going to end up being C plus D times A, C plus D times B inside the vector U. And then we know, again, once we have real numbers, we know we can distribute real numbers. So we do CA plus DA, CB plus DB. And again, now we can split them up. And factor out the D and the C again, and then be able to show what we were hoping. So this is C times AB plus D times AB, and so that's C times U, D times U. Okay, great. 9 and 10 are a little more straightforward. So 9 is telling us we should be able to reorder scalars multiplying a vector. And then 10 tells us when you multiply the scalar 1 times a vector, it should say the same. So those things are a little more easy to show, a little quicker. So 9 would look like C times du, and then we want to write out the components, rearrange things, and regroup. So this is going to be C times dA dB. And then we multiply the C in there. I'm sorry, then we factor out the D. And then look, C and D are now grouped together times U. And that's what we're hoping to show. Forgot to put some checks. So check, we checked that one, we checked that one, we checked that one, we checked this one, that one's good. Last but not least, does number 10 work? It does. Let's see. 1 times U is going to be 1 times AB. You multiply each entry by 1 and it stays the same. And so this vector stayed the same. Check. And so the sort of final punchline takeaway that you might want to write here is all 10 axioms hold, so R2 is a vector space. And anytime you want to show a vector space, it follows the same property, or the same process, I mean. You write down 3 vectors in the space, 3 arbitrary vectors, and then you go through each property, write down the individual components, rearrange things, regroup things, and show that all the 10 axioms end up holding. And that's what we'll do on the next page with a more abstract vector space. Before we do that, I wanted to show an example of something that fails. And so the next problem on this page is asking to show that the union of the first and the third quadrant is not a vector space. And so if you want to show something's not a vector space, like it says on the first page, all you need to do to show something's not a vector space is just show that one of the 10 things here doesn't hold. And so let's take a look at this one. So let's think about this one. So show that the union of the first and the third quadrant in the xy plane is not a vector space. So the idea is, if we're talking about R2, and this is the xy plane, so it's like yx, of course, and we're saying V equals the union of the first and third quadrant. So the union of this quadrant with this quadrant. And so again, our vector space V is everything that's in both of those quadrants. And so if this is not a vector space, if it was, we'd be able to show all the properties. If it's not, we should just show that one of them fails. And so an interesting way we can write this vector space, V, another way we could write it is, it's all ordered pairs x comma y such that when you multiply x times y, you get a positive number. Right? So everything in the first quadrant is positive, so when we multiply them, we get a positive number. Everything in the fourth quadrant is negative, and so when we multiply 2 negatives, we get a positive number. And so this is a way we could characterize those 2 quadrants. When we multiply anything in the second or fourth quadrant, we get negative, right? And so that's another way we could think about that. And so a number of the properties fail in this one. I would maybe take a second and think about which of these 10 properties on the first page are going to fail if we try to think about the union of the first and the third quadrant. Maybe pause the video real quick and think about that. Hopefully you paused it and thought about that. I'll tell you the ones that fail, and then maybe you think about why. So number 1 fails, number 4 fails, and number 5 fail, at least. Maybe think about why. So number 1, 4, and 5. So number 1 fails because we can pick 2 vectors in the space, add them together, and it won't be in the space. So let's start with number 1. So 1 fails. Get another color here. 1 fails. So this is why. Let's pick 2 vectors in the space, add them together, and show it's not in the space. This is what's called a counterexample. So we just need to show 1 counterexample, and then this isn't a vector space. So let's U be 1, 2. So that would be up here in the first quadrant, right? And V, let's let V be minus 3, minus 1. This would be in the fourth quadrant. Let me be clear about that. This one's in quadrant 1. This one's in quadrant 3. When we add them together, we get something that's in quadrant 2, right? So these are in quadrant 2 and 3, and so U and V are in our larger space V. But when we add them together, 1 plus minus 3 is minus 2. 2 minus 1 is 1. And so we get minus 2, 1, and that's over here in the second quadrant. So we added 2 things together that were in the space because it's in quadrant 1 and quadrant 3. But we added them together and we got something that was outside of the space. And so since U plus V is not in our space V, 1 fails, and so our space is not a vector space. All you have to do is show one of them fails, and so we already know it's not a vector space just because we can show that number 1 fails. But let's talk about the other ones that fail too, at least a couple of them at least. So 4 fails because we don't have 0 in the space. If we're talking about the first and the third quadrant, the 0 vector, which we know is 0, 0, is not in there, right? So 0, 0, let me do it with the color that'll show up here. The 0 vector exists right here. And that's not in the first or the third quadrant. It's like on the axis. The axis, excuse me. And we specifically define the space as being in the quadrant, not sort of not counting the lines, right? We want to multiply the values and get a positive, and if one of them's 0, we won't get that. And so 4 fails because it's 0 is not in the first or the third quadrant. So 4 fails because the 0 vector is not in quadrant 1 nor quadrant 3. And so that means it's not in our space. And then I also said 5 fails. So 5 fails because it's kind of like a technicality here. If you might have an additive inverse that exists. The additive inverse does exist, but it needs to get us back to u, and u needs to be in the space. I mean 0. Right, so we have an additive inverse that sends us to a 0 vector, but it doesn't send us to a 0 vector from the space. So maybe I won't write that down. That's kind of a technicality. 1 and 4 are kind of the most obvious one. 5 kind of fails just because 4 fails in some sense, but that's sort of more of a technicality, so I'll just leave it like that. But very clearly, 1 and 4 fail, and so that's more than enough to show that this is not a vector space. Okay, to kind of drive this point home a little bit, I'd like to look at an abstract vector space. And so this is a really important part of linear algebra, is thinking about how we can apply some of these concepts beyond Euclidean spaces Rn. So Rn is what we're used to dealing with, but there are lots of spaces out there other than Rn, such as Pn. So this is a very common abstract vector space where it's saying, let's read the definition here, let Pn be the set of polynomials of degree at most n. In other words, Pn is some arbitrary n degree at most polynomial. And so we've got t's here, which are the variables, and then the a's are the coefficients. And so the idea is like the p tells us, when you see a script p like this, that means we're dealing with a polynomial space. Polynomial space, and then the n part tells us the degree of the polynomial we're dealing with. And so in this specific example, we'll think about, is P2 a vector space? So P2 would be polynomials of degree 2 at most. So polynomials of at most degree 2. And so if we want to show this as a vector space, spoiler alert, it is, then we would want to go through the 10 axioms once again and show that they all hold. So yep, it's a little bit tedious, I understand. I'm going to try to do this one a little bit quicker, maybe a little bit less commentary and a little more just kind of going straight through it. Again, normally when I run the class, I have people try this themselves. So if you feel comfortable trying this one, you might want to just start writing it down maybe as I'm writing it down, or maybe pausing it, trying it yourself, and then forwarding the video, seeing if you get the answers correct. I really strongly recommend you try this on your own. You know, one of the best ways to learn online is going to be to take ownership over your learning and try things like this. So please do. If you want to let me set it up, that's fine too. So the first thing we need to do is pick 3 arbitrary elements in the space, right? So we want to go through the 10 axioms. And so in order to do that, we need a u, a v, and a w in the space. And so let's pick 3 vectors, u, v, and w. So let's let u be a0 plus a1t plus a2t squared, right? That's some arbitrary degree 2 polynomial. Let's let v be another arbitrary degree 2. So how about b0 plus b1t plus b2t squared? That's another arbitrary degree 2. And let's let w be c0 plus c1t plus c2t squared. And so we've picked 3 arbitrary elements. In all 3 of them, the A's, the B's, and the C's are scalars. They're just coefficients. And the T's are the variable. And so we're just going to go through those axioms one more time and show that they all hold. So I'm going to start by adding two vectors together, u and v, and seeing that it stays a degree 2 polynomial. So when I do u plus v, I add u plus v together. And then I want to show that this is still a degree 2 polynomial. Well, the biggest power is still a square, and we can see that even better by just regrouping things together so that we can group, say, the constant together. There's our constant term. We could group the t term together, and then we could group the t squared term together. And so this is still, look, this is still a degree 2 polynomial. So this is still in, oops, not R, it should be P2. And so check, we showed that one. We added 2 arbitrary degree 2 polynomials and it stays a degree 2 polynomial. Let's do property 2. Property 2 tells us we should be able to change the order in which things are added. So when we look at u plus v again, I'm going to write down u plus v again, same thing right above. And since we have just a bunch of terms being added when we do u plus v, this is u plus v, we can just take these ones and put them in front of the other ones, and then it becomes v plus u. Right? So we literally just like change the order because it's just a bunch of terms being added now. And this is exactly what we wanted to show. So number 2 got shown. We showed number 2. Number 3 says we should be able to regroup the way things are added. So let's add u, v, and w. Group them u plus v first, and then it'll be a bunch of terms, and we can just regroup them and show that we did that. This is mostly just a lot of writing. This shouldn't be terribly hard to think about. So u plus v being grouped first would look like what we've written down a couple times already. There's u plus v being grouped. Then let's add w. And then, now that we have that, we can just, this is a bunch of terms just being added, we can just drop the parentheses here and then add them wherever we want to add them. So I'm going to drop all the parentheses and then group v and w together instead. So I'm just going to write u by itself and then group v and w. And we did it. This is now u plus v plus w. Check. What do you think the additive inverse is? That's what we need to show for 4. I mean the 0 vector, excuse me. The 0 vector for number 4. What is the 0 vector in P2? It should be something that when we add it to vectors, they stay the same. Well, it's just the 0 polynomial. So for number 4, the 0 vector is 0 plus 0t plus 0t squared, right? This is an at most degree 2 polynomial. This is in P2. And when we add this to an arbitrary vector, it stays the same. So we found what the 0 vector is. I should have mentioned this too. You know, we're using the word vector. We've been almost conditioned to think of vectors like in Rn, right? Like from the last page, right? This is a vector 2, 1. This is an arbitrary vector a, b. These are vectors in Rn, and the idea behind showing you an abstract one is to sort of open your eyes to, okay, we can have vectors that are polynomials. Vectors just mean an element of a vector space. A lot of the times we deal with Rn as a vector space, but it doesn't have to be. Okay, let's keep going here. So number 5 needs to be the additive inverse, and the additive inverse is just making all the elements negative. So if the coefficients. So if this is our u vector, the same u we've been dealing with this whole time, then the minus u vector that would get us to this 0 polynomial when we add them is going to be minus a0 minus a1t minus a2t squared. That's the additive inverse. Okay. Number 6 says we need to have the space closed under scalar multiplication. So let's multiply by a scalar and see that we stay in the space. And so number 6, let's multiply c times u. So c times u is going to be ca0 plus ca1t plus ca2t squared. And we can just relabel this as a new a0, like a0 star. This is some new a1 star. This is some new a2 star. And then we could say, well, look, this is still a degree 2 polynomial. In other words, this is still in P2. So check, got that one too. Oh, we also checked the last one off, forgot to check it. All right, we're more than halfway there. We can push through and get this. I know these vector space things are a little bit tedious sometimes, but I do think it's worth showing a couple of them, especially an abstract one like this. 7 and 8 are the distributive ones here. I am going to not write out all the gruesome detail to save space here. We're running out of space. But the first one says we should be able to distribute, oops, that should be a v, a constant through the sum of 2 vectors. And we know that when we do that, it's going to end up looking like this. We distribute the c to both elements. Should be a c there. And then just group them separately and show that this is actually cu plus cv. Right, we would factor the c out of each one first, and then group them like that. But I'm running out of space here, so hope you see what I mean there. And we would do a very similar thing with 8, right? So 8, we want to show this can be distributed. And the way we would do this is we would distribute the constant through u first. So it would be kind of like c plus d a0, c plus d a1t, c plus d a2t squared. And then once we have this set up, we know that we can distribute real numbers like that. And so we would distribute the real numbers and then regroup them with the c's and the d's separately. So we'll distribute the real numbers and then group the c's and the d's separately. So it'll be ca0 plus ca1t plus ca2t squared. That's going to be our c times u. And then we have the d's separately. And so this is cu, this is du. And so that one worked. Okay, let's finish off the last couple. Number 9 tells us we should be able to regroup scalar multiplication. So let's look at c times du. Well, first thing we would do is multiply d times u. And so we'd have c times dA0, dA1t, dA2t squared. And then we can multiply the c through there and get exactly what we're looking for. So cdA0, cdA1t, cdA2t squared. And then what we could do is factor the cd out and then have it multiplied by u. So I'm going to skip a couple steps here and just say, wait, we could factor out the cd, have that separately, and then it would be multiplied by the vector u. And so that one works. And lastly, when we multiply a vector by 1, it stays the same. So 1 times u would just be 1 times our vector u. 1 would multiply each one of those constants. I'm just going to write this one out for the heck of it. And we know that when 1 multiplies one multiplies a real number, it stays the same. And so this just ends up being exactly the same. So we showed that this did not change. Okay. So since all 10 property axioms were satisfied, this is a vector space. All 10 axioms satisfied. This implies P2 is a vector space. Whew, okay. I know that was a lot of writing. And showing vector spaces is pretty tough. You know, on tests and things like that, sometimes I might ask you to show one thing as a vector space, but more often than not, then I ask specific questions about vector spaces, or maybe I say like show these 3 properties hold instead of showing all 10. So I'll ask you to do like a subset of them or something. Just be aware that it take a long time to do, and so I don't ask like long questions like this on tests. But you should be able to understand them, and on homework you ask specific questions about them, and you should be able to reproduce at least a couple of these on a quiz or a test. Okay. So let's keep going with subspaces now, which is easier to show, and something that comes up, maybe questions that are related to subspaces I feel like come up a little more often than vector spaces, especially in future classes and quizzes and tests and things like that. And so let's get the idea down here, and we're going to draw a little picture at the top of this page here, so that's why I want to show that. So here we go. Let's read what it says. So subspace. Oftentimes we're presented with a set that's a subset of a vector space. In these instances, we already know most of the axioms hold of subspaces, and so we have to show fewer things to show something as a subspace. And so let's read the definition, and we'll draw a picture here that represents this. So a subspace of a vector space V is a subset H of V that has these 3 properties. And so we're showing like a subset of the properties on the last page, because since we have a subset of a vector space, we already know most of the properties hold. And so since we know most of them hold, we just need to show that the 0 vector of the larger space is in the smaller space, that the smaller space is closed under addition. In other words, when you take 2 elements in the smaller space, you should be able to add them together and stay in the smaller space. And it needs to be closed under scalar multiplication. So you take a random vector in the smaller space, and when you multiply it by a scalar, it should stay in there. So the idea is we have some larger vector space. Say they're calling it V, and then H is going to be inside of that, so it's a subset of it, so it would be a subspace. This is going to be the H. And so one specific example could be like, we know Rn is a vector space, so for example, we could say the larger space is R3. Right? And so this is elements that look like x1, x2, x3, 3 elements in there. Well, if that's our larger space, a subspace of that could be vectors of the form, so H would be our subspace. It might be vectors of this form 0, x2, x3. And so it's a subset of the vector space because it's still 3-dimensional, right? So we're still in R3, but we're specifying that the first entry should be 0. And so we're taking a subset of all vectors that look like x1, x2, x3 by saying the first entry has to be 0, for example. And so it's inside the larger space, but it's a smaller group of vectors since it's specifying something about it, just as an example. And this would be a subspace because it satisfies these three properties. The zero vector is in here, it would be closed under addition, and when you multiply it by its scalar, it would also stay in that space. And so this is an example of a specific vector space. But again, the idea is like, since the space we're talking about, H, is inside the larger vector space V, we only have to show that 0 is in there, that it's closed under addition, and that it's closed under scalar multiplication. Or, the other way to say that, if it's not a vector or not a subspace, we just need to show that one of those things fail. Okay, and so on this page below here, I've got an example of one that is a subspace and one that's not. And so let's take a look at those. So let's let H be the set of all polynomials P sub n such that P of 0 equals 0. And so this is saying every single polynomial such that when you plug 0 into the polynomial, you get 0 out. And so if this is an arbitrary, let me write down an arbitrary polynomial. So a0 plus a1x plus a2x squared plus dot 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 anx to the n, where the a's are scalars. So that's what just a generic polynomial looks like, right? Some degree n polynomial. Well, if we want to plug a 0 into all the x's and have the result be 0, what does that mean about the coefficients? It means something specific. Maybe take a second and think about that. Pause the video if you need to real quick. Well, if we want to plug a 0 in and get a 0 out, that means that this term, the a0 term, needs to be 0. And so the question is this a subspace of Pn? So we're looking at polynomials where the constant value is 0. And so let me write that down first. So first, if P of 0 equals 0, then that means P of x has the constant value a0 be 0. All right, that's what we're saying here. And so let's go through and see, is the 0 vector in there? Can you add two arbitrary vectors together? Do they stay in there? Can you multiply by a constant and stay in there? So let's start with A. Use another color here. Is the 0 vector in there? Well, we know the 0 vector is the 0 polynomial, right? And so if this is already specified to be 0, we can just make the rest of the a 0, and we have the 0 polynomial. And so we can let a1 equal a2 equal dot dot dot. All of them are going to be 0. And then that would mean the polynomial, the 0 polynomial, is in H. Let's add two arbitrary vectors together and show that it stays in the space. So let's let our third vector be the sum of two arbitrary smaller vectors. Arbitrary vectors in the space, excuse me. So we're going to add two vectors together. Do we get a third one that's in the space? So my first vector that I'm going to add together is going to be this one. Okay, so that's my P2. And then I'm going to add to it an arbitrary vector with B's instead. I'm going to put a 1 there. So here I am adding two arbitrary vectors in the space. And when we do that, we get a degree n that still satisfies P of 0 equals 0, right? So if I do that, then our P3 ends up being a1 plus b1x, a2 plus b2x squared, dot dot dot, an plus bn x to the n. And notice that we don't get, when we plug a 0 in, all these x's become 0, and so we still get P of 0 equals 0. So notice P3 of 0 is going to just be 0 plus 0 plus 0 equals 0. In other words, i.e., still in the set. And so the second property is satisfied. So we satisfy the first two properties. And the third one is also going to be satisfied. So let's multiply an arbitrary vector by a constant and show that it's still in the space as well. And so lastly, C times P1x is going to be CAX1, A1x, CA2x squared, CAN x to the n. And notice when we plug a 0 in, we still get a 0 out. So CP1 still in H. Check. And so since all three properties are satisfied, we have a subspace. So again, since we had a subset of an existing vector space, we just needed to show the three properties to show that we ended up with a subspace. And very similar to the other, the vector space notes, if we want to show something is not a subspace, we just need to show that one of the properties fail. And so that's what's going on with the one at the bottom of the page here. It fails because at least one of the properties above there fail. So I'm going to just read this one while the definition is still on the page here. Let's read the one at the bottom of the page here. Let W be the set of all vectors of this specific form, where A and B are arbitrary numbers. So you pick some random A and B, you plug it into those two spots. The first entry is always 1, and then you get a vector in the vector space. And the question, is this a subspace of R3? So it's a subset of R3 because we've got three entries in the vector, right? But we're specifying certain things about the entries, and so that's why it's a subset of R3. And so maybe look at this and think about A, B, and C up here. Which one of those things, so the answer is this thing, is it a subspace? The answer is no. Which one of these A, B, and C fail? Take a quick second and think about that while I add a couple notes here. So first of all, this is a 3 by 1, and so W is a subset of R3. The question is it a subspace? So maybe you've had a second to think about that. I don't know, maybe pause the video if you're still thinking about which one of those properties fail. But the answer is W a subspace? No. All three conditions fail. And I would like to show you why all three fail. Again, all you need to show is that one of them fail. And so, once you show one, you can just be done on the test or something. But I want to show you that all three fail. So 0 is not in the space. So 0, 0, 0 is the 0 vector, right? But if this is specifying that the first entry needs to be 1, then we can never get the 0 vector. So 0, 0, 0 is not in W because the first element has to be a 1. And so A fails right off the bat. Let's talk about why B and C fail. So B says you should be able to add two vectors together and it stays in the space. And C says we should be able to multiply by a constant and it stays in the space. And so B fails because this. So B. Let's pick an arbitrary vector in the space, add two of them together. So let's let U be 1, 3a1 minus 5b1, 3b1 plus 2a1. So this is my first vector in the space. And let's pick another arbitrary vector in the space, just using 2's instead of 1's. So these are two arbitrary vectors in the space, picking different a's and b's, basically. And if we added them together, the second and the third entry would actually look okay, but the first entry you add together and it would end up being the number 2. And this space specifically says we need to have a 1 in the first entry. And so if we did U plus V, we would end up with, and so I'm going to do u plus v, but also rearrange things and factor it. So I'm going to skip a couple steps here, but if we did u plus v, we'd get a 2 in the first spot. We would get this in the second spot. And then this in the third spot. And so again, this space specifically says we need to have a 1 in the first spot. And what we just showed was when we add two arbitrary vectors together, you get a 2 in the first spot. And so this fails because it's not a 1. But this is okay. And the second and third entry are actually okay. They follow the correct form. So what the second and third entry say is you should have 3 times a right here and then 2 times a right here. Right? So 3 times a1 plus a2, 2 times a1 plus a2. So those two things match, and so that follows this form. And then 5 times b and 3 times b, and so those two things match. And so it still follows the form in the second and third spot, just not in the first one. And then the last property also fails. So if we multiply a scalar times u, we'd end up with a c in the first spot. We'd get c 3a1 minus 5cb1, 3cb1 minus 2ca1. And so again, like these two entries, the second two entries are okay. It's the first entry that fails. And maybe think about why. Again, we need to have a 1 in here. So why does that fail? Well, c is some arbitrary scalar. It can be any number that we want. And so if c is in the first spot, it could be something not 1. And so if c is not 1, this fails. So this fails because when c is not equal to 1, then this entry is not equal to 1. And so all three properties on this particular space fail, which is why it is not a subspace. Okay. I don't want to just leave one more page on this chapter, so I'm going to finish this one and we'll probably get close to 75 minutes here. But I will take a look at the next section real quick. The next section will be, I think, considerably shorter, and so we'll make up time in the next section a little bit. But let me finish this section with a theorem and a quick application of that theorem. So the theorem says, let v1 to vp be vectors in a vector space. Then the span of those vectors ends up being a subspace of v. And that's nice because if we have a group of vectors and we can rewrite it as the span of vectors, we know it's a subspace is how we use this property. And so I'm going to sort of do a quick proof of this, where I'm going to go through the three subspace properties. And so let's suppose that v1 and v2 are in our vector space V. And let's let our subspace be the span of those two things. Well, we know the span of elements are linear combinations. So C1 V1 plus C2 V2 for any C1, C2 scalars. So you pick any number for C1, C2, and that's some linear combination of V1 and V2, and so that would be in the span. And so if this is truly a subspace, so the claim here is that H, which is the span of those things, which is this, is a subspace of V. Well, if that's the case, we should be able to find the zero vector, we should be able to add two vectors together and show that it's still in the span, and the span should be closed under scalar multiplication. And so the question first becomes, is the zero vector in there? Well, if we just let C1 and C2 be 0, we get the zero vector. So if those two things are 0, then we'll get 0 V1, 0 V2, And so we end up with the 0 vector. Excuse me. And so the 0 vector is part of the span. And so 0 is in H. So we did show that the 0 vector is in there. The next thing we would want to show is that it's closed under addition. I'm sorry, did I do A, B, C or 1, 2, 3? It should be A, B, C. So this should be A. And then this one should be B. Sorry about that. So let's pick two arbitrary elements in the scalar, so in the span. So let's U be C1 V1 plus C2 V2, and let's let V be C3 V1 plus C4 V2. So U and V are both elements in the span because they're just two different linear combinations of U and V. And notice that when we add them together, I'm going to add them together and rearrange things and group them. So when we add them together, I'm going to group the V's together and factor it out. So we'd get this. And then I'm going to group the V2's and factor it out. So we'd get C2 plus C4 V2. And so this is some other linear combination of U and V. I mean V1, V2, right? In other words, we could let this be like C5, and this is some other C6, right? C1 plus C3 is some other constant. C2 plus C4 is some other constant. And so we could just rewrite this then as, say, C5 V1 plus C6 V2. And so this is some other linear combination of V1, V2. In other words, U plus V is still in the span. Right, this is some other linear combination of V1, V2, and so we added U and V, and it was still a linear combination, so it's in the span. Lastly, we can just multiply by a constant and show that it stays in the space, right? So when we multiply C times U, I'm going to use this same U that I just did in the last part, we would get C times C1 V1 plus C times C2 V2. And again, we could just relabel this as some other constant. So C times C1 is going to be like C3, some other constant. And C times C2 might be, say, C4. And so we get some other linear combination. And so it's still in the span. And so the second property got showed, the third property got showed, and so A, B, and C were satisfied. And so this is just sort of proving to you that if we have the span of vectors in a subspace, we know it's also a subspace as well. Excuse me, of the span of vectors in a vector space, we know that it itself is a subspace. So the idea is that since A, B, C are satisfied, H equals the span is a subspace of V. And so this is a nice property of subspaces, because if we're able to rewrite a vector space or a subspace as the span of vectors in a vector space, we don't have to show anything. We can just use this theorem and say, hey, the theorem tells us it is a subspace. And so we see these in homework problems, and I ask them on test questions and things like that. So this does come up, knowing how to do this. And so like a really easy example would be what it says right here. So let's let W be the set of all vectors of the form that look like this. So we're in R4 here because there's 4 entries in this vector. But it's a subset of R4 because we're saying we're sort of specifying things about what the values need to be. So it's saying like the second entry has to be 0. The first entry, you pick A, B, and C, and you can fill in vectors in this space. But the nice thing is you can break this vector up and make it look like the span of vectors in R4, and then just use the theorem. And so let me show you what I mean by that, and this will be the last thing on this video here. So W is that, right? So I'm going to rewrite that. It's vectors that look like this. And I'm going to break this up into the A, B, and C components as different vectors. And so I'm going to do that in one step here, and hopefully you see what I mean here. So the things that have A in it are 4, 0, 1, 0. The things that have B in it would be 3, 0, 3, 3. And then the C breaks down into 0, 0, 1, negative 2. Where A, B, and C are any scalars. And so, hey, this is the linear combination of three vectors in R4, right? Like 4, 0, 1, 0 is V1, 3, 0, 3, 3 would be V2, and 0, 0, 1, negative 2 is V3. And A, B, and C are arbitrary scalars, and so we're doing a linear combination, or the span, of three vectors in Rn, R4 specifically, right? So thus, W is the span of those vectors. And each V sub I is in the vector space R4. So we have our W is the span of vectors in a vector space, which follows exactly what this theorem is, right? Our vector space is the span of V's, and the V's themselves are in a vector space. And so that means our space, by that theorem, is a subspace. So thus, W is the span of these three vectors. Each of those vectors is in R4, which is a vector space. Thus, by theorem 1 above, W is a subspace of R4. And so again, this just provides a nice way to quickly show something is a subspace if you happen to be able to rewrite it as the span of vectors. And so we do see this property get used in the homework, and it does pop up on tests. So it is something that you want to know how to do. Please let me know if you want me to clarify something about that.